Okay, so what we are going to do today is called this maximal matching of edges. Okay, so an application of this could be like you're given, say, um, set of students or set of employees, and you want to pair them so that they can work together as a team. So you don't want to arbitrarily pair people. So you want some you want some kind of the people to like working with each other, right? So you do a survey and find out some preferences of the people. So then, so like this here. So node 1, so each node corresponds to a person. So node 1 says he or she prefers to work with nodes 2, 5 and 6. And node 1 may also prefers to work with, say, node 4. But node 4 doesn't say prefer node 1. So you have an edge between two people if they really prefer each other. So if just one person prefers the other person and that person doesn't prefer this person, we don't have an edge between them. So so like that you capture this graph, and then what we want to find out is we want to pair, okay, so every node with some other node. Now we want to pair them in such a way that no node appears in more than one pairing. Okay, so that is what is called a maximal matching. So by definition, a maximal matching is a set of independent edges such that, okay, the addition of one more edge to the set violates the property of matching. So matching is simply this: 1, 2, 3, 4 and so on, such that no node appears more than once. So for example, in this case 1, 2, 3, 4, 1 doesn't appear anywhere else in this pairing, 3 doesn't appear anywhere else in this pairing. So that's simply called a matching. Okay, so matching by definition is a set of independent edges such that no two edges have a common end vertex. That is same as telling no vertex appears more than once. Okay, so no two edge should have the same a common end vertex. Is that clear? That's a definition of matching. Now what we call as a maximal matching is some set of edges, okay, that is satisfying the property of matching, but if you add one more edge to that set, it will violate the property of matching. So look at this set 1, 5, 2, 7, 3, 4. It is satisfying currently the property of matching because no edge has a common end vertex. 1, 5 doesn't appear anywhere else, 2 doesn't appear anywhere else, 3 doesn't appear anywhere else. So no two edges have a common end vertex. So that is a matching. Now if I add one more edge to this set from this graph, so all these three edges are taken from this graph: 1, 5, 2, 7, 3, 4. All these three edges are from this graph. There are a lot of other edges also available in this graph. But if you add any other edge to this set of three edges, it is going to violate the property of matching. You can check. Let us add the edge, say 1, 6. 1 is already here. If I add the edge 5, 6, 5 is already here. If I add the edge 2, 3, both 2 and 3 are already here. 7, 8, 7 is already here. 4, 8, 4 is already here. So if I add any edge, so given this three edges, set of three edges, if I add any other edge in this graph to this set, it's going to violate the property of matching. So that's the definition. It's a set of independent edges such that the addition of one more edge to this set violates the property of matching. So such a set of edges is called a maximal matching. So if I take again this set of edges 1, 6, 2, 7, 4, 8, given that my set has these three edges, if I add any more edge from this graph to this set, it's going to violate the property of matching. Now I can come up with these four edges as my set of edges, and it will satisfy the property of matching because no two edges have a common end vertex. And now if I add any more edge to this graph, it's going to violate the property of matching. Similarly, this set of edges. Now you see here there are 8 vertices in this graph, and our goal is to pair a vertex with some other vertex, right? So these are the pairings. So 1 is paired with 5, 2 is paired with 7, 3 is paired with 4, and so on. Now, so we have 4 maximal matching combinations listed here, and among these the first 2 match only 6 of the 8 vertices, right? So there are 6 vertices across these 3 edges in the first and second set, whereas the last 2 set of edges really match each vertex with some other vertex, right? So there are 8 vertices, so you have 4 edges in each set, and that's the best we could expect. So we can call the last 2 set of edges to be also called the maximum matching. So that's the kind of a small difference in terminology. A maximum matching means we have accomplished the best, the sense that for every vertex we have matched it with some other vertex in the given graph. So that means if your graph has say v vertices, v means the number of vertices, then if the matching that you come up with has v over 2 edges, and given that say the v is even number, so in this case v is 8, it's an even number, so v over 2 is 4, and the last 2 matchings have 4 edges, which is equal to v over 2, then we can say we have found the maximum matching for the graph. Now if v is an odd number, of course then we cannot definitely for sure match every vertex with some other vertex, right? Because it's an odd number. So we are going to have only v over 2 minus 1 pairing. So if the graph has 7 vertices, we are going to only have 3 pairs of edges. But still we can call that as a maximum matching because the graph has odd number of vertices. So that's the difference across these 3 terminologies. So let me just repeat again. A matching means some arbitrary set of edges such that if I add any such that for any 2 edges there's no common end vertex. That's simply a matching. Now maximal matching means a set of edges that satisfies the property of matching, but adding any more edge to that set will violate the property of matching. That's called a maximal matching. So this first any of these 4 satisfy this property of matching, but adding any more edge to any of this will violate the property of this matching. So 1, 5, 2, 7, 3, 4 satisfies the property of matching because no 2 edges have a common end vertex. But if I add any more edge from this graph to this set, it will violate the property of matching. Same thing with the other 3 cases. Now a maximum matching is a set of edges such that it satisfies the property of matching and we have paired every vertex with some other vertex. So a maximum matching first of all needs to be a maximal matching, because if you add any more edge to the set, it's going to violate the property of matching. So a maximal matching is a maximal matching, but the reverse need not be true. A maximal matching need not be a maximum matching, because like the first 2 cases are maximal matching, but they are not maximum matching. Whereas the last 2 is both maximal as well as maximum matching. Okay, so is this terminology clear before we proceed? Any question? Okay, so let me see. Alright, so now what we want to find is, given a graph, we want to find what is called the maximal node matching. Okay, so that means basically we want to find a maximal matching such that the number of nodes that are paired or matched is the maximum. Okay, now we can call it as a maximal node matching in general instead of calling maximum node matching, because we cannot guarantee for every graph you're going to find a maximum matching. So let us keep it as maximal instead of maximum. Okay, and that's the application I just mentioned earlier. Given a network of people, we can work with each other. We want to maximize the number of two-member teams. So that's one application where this algorithm can be applied. So let us take this same graph again that we saw here. So this is a maximum matching because it has all the 8 vertices matched, each vertex to somebody else, and that's the best we can do. That's also then a maximal node matching. Now look at this graph. It's a graph of 8 vertices. Now the matching I have listed here is having only 6 vertices covered, so it cannot be called a maximum matching, but that's the best we could do on this graph, the second graph on the right side. So we could call it as a maximal node matching for this graph. Okay, 1 5 2 6 3 7 is a maximal node matching. Now 1 2 6 7 is also can be called as a maximal matching on this graph because it satisfies the definition of maximal matching. Means it is currently a matching, no two edges have a common end vertex, and adding any other edge from this graph will violate the property of matching. So for example, you can try 1 5, 1 is already here, 1 6, 1 6 is already, 1 is already here, 2 3, 2 is already here, 3 7, 7 is already here, 4 7, 7 is here, 7 8 is already here. So you cannot add any more edge to this set of two edges. So it is called a maximal matching, but we know this cannot be called as a maximal node matching because we have another combination of edges that covers 6 of the 8 vertices, whereas this covers only 4 of the 8 vertices for this graph. So this cannot be called as a maximal node matching. So that's again how to understand the differences between maximal matching, maximal node matching, and maximum matching. So we'll focus on this maximal node matching. That's what we want to find out. Okay, so let us take the second graph here and work out the algorithm. So in order to do this, we want to go through an iterative process of picking or accumulating one edge at a time to the set of edges. So it depends what set, because you see here it depends really on what edges I pick to be part of my set. So again, each time I said, given this set of edges, if I add one more edge to this set, it will violate the property of matching, right? So given that I have picked say 1 2 6 7, I cannot put any more edge to this set and still satisfy the property of matching. So now what we want to accomplish is to pair as much as possible every vertex with some other vertex, right? So we want to maximize the number of matchings we find out. So that's the objective. So it's really important we take care of what edges we start putting in this set. So in order to decide the right edge to be included in this set, or the more appropriate edge to be included in this set, we will measure something called the coverage weight for each edge. Okay, and the coverage weight of an edge is nothing but the number of edges adjacent to that edge in the graph. So what I mean by adjacent edge, so for example, for this edge 1 2, the adjacent edges are edges either connected to 1 or connected to 2. So the adjacent edges of 1 2 are going to be those connected with 1, say 1 5 1 6, or those connected with 2, say 2 6 or 2 3. So these are the 4 edges that are adjacent to the edge 1 2. So we are going to find the number of adjacent edges for each edge in the graph, call it as the coverage weight, and then among those edges we have to pick one edge to be included in our set and then keep going from there. So which of these, what you call like 10 edges here, we should pick? That's what we need to decide now. Okay, later I'll tell an easier way to find the coverage weight. You don't have to really go to the graph and find the number of adjacent edges, but that's what the coverage weight is, and I'll tell you a better way to calculate these numbers. But given that these are the coverage weights now for these edges, which of these 10 edges we should pick to be part of our maximal node matching set of edges. That's what we need to decide. Given those numbers, there are two choices. We can pick the edge that has the largest coverage weight. In this case, the largest coverage weight is 6, and that corresponds to edge 6, 7. And let us see what happens if we do that. If we pick the edge 6, 7, that means if it has a coverage weight 6, so that 6 means it has 6 adjacent edges. So these are the 6 adjacent edges of this edge 6, 7. So if I include the edge 6, 7 to my set of edges that are part of the maximal node matching, then these 6 edges are automatically ruled out from being considered, because to satisfy the definition of matching, no two edges in the set that I pick or build up should have a common end vertex. So if I pick any of these 3 red edges that are adjacent to 6, 7, 6 is going to be there as an end vertex. Similarly, for these 3 edges, 7 is going to be an end vertex. So automatically, if I pick this edge 6, 7, these 6 edges will automatically get ruled out. And that means we have only 3 more edges in this graph to consider as candidates to be picked for the set of maximal node matching. And that itself reduces the chances of maximizing the number of edges we pick up for this set. So that's why picking the edge with the largest coverage weight is really a poor choice. Okay. On the other hand, let us consider picking an edge with the smallest coverage weight. And the smallest among the numbers is 3, and we have a tie. We can break the tie in any order, it doesn't really matter. So let us say I pick the edge with the smallest coverage weight, which is 2, 3. Let us say I pick 2, 3 and break the tie in favor of 2, 3. So when I pick 2, 3, its coverage weight is 3. So these 3 adjacent edges are those that are getting ruled out from being considered for the next edge to be picked up. So once I pick 2, 3, 2, 3 is of course part of the set of maximal node matching, but these 3 edges cannot be considered anymore. So the other edges are still available for being considered. So you want to maximize the number of edges that are still available for being considered in each iteration. So that's a greedy strategy, and we will see that it does find us the maximal node matching. Okay, so that's the strategy we are going to employ here to find maximal node matching. Now let me enter the formula. I thought I had it here. So the formula that we can use for the coverage weight is this. So the coverage weight of an edge UV is the degree of U plus the degree of, I'm going to put it somewhere in the slide later, degree of V minus 2. So this is the formula for the coverage weight for an edge. Okay, let me put it here. Okay, so let us pick the edge 1, 2. So its coverage weight according to the formula is the degree of 1 plus the degree of 2 minus 2. So the degree of 1 is 3, the degree of 2 is also 3, so 3 plus 3 is 6 minus 2, that is 4. The edge 1, 5, the degree of 1 is 3, the degree of 5 is 2, so 3 plus 2 minus 2 is 3. So basically when you do the sum of the 2 degrees, so you are considering the edges, so for the edge 1, 2, you are considering the other edges that are incident on node 1. So, and you see you are looking at the edge 1, 2, so you should not consider that edge, you are looking only at the other edges. So that's why you take the degree of U, do a minus 1, because this edge 1, 2 should not be considered as part of degree of 1. Similarly for node 2, you are considering the other edges incident on node 2. so you should exclude this edge 2, 1 from your calculation. So that's why you're taking the degree of v minus 1. So it's degree of u minus 1 plus the degree of v minus 1. So that's why the minus 1 put together is minus 2. So degree of u plus degree of v minus 2. So you should be able to interpret this formula. So as a good, you are all graduate students, so you should be able to interpret the things that are given to you. So the formulas and stuff like this. Not only in this course, in any other course you take. You should not just take it as a formula and memorize it and use it. Why the formula is like this? So in this case, that's what it is. So you should be able to explain why we calculate coverage weight like this. Because we want to find the number of edges adjacent to an edge. And that's based on the edges that are incident on the edge and the number of such edges that are incident on the two end vertices. Okay. Any questions so far? Okay. Alright, so let us go continue. So I pick the edge with the minimum coverage weight. So these are the coverage weights of the edges, and I say pick edge 2, 3. So when I pick 2, 3 to be part of my set, it's adjacent edges, which are the 3 adjacent edges, because its coverage weight is 3. So you should make sure you delete those edges from your graph. So the 3 adjacent edges of 2, 3 are 2, 1, 2, 6 and 3, 7. So remove them from your graph. So that's the updated graph for the next iteration. So now redo the numbers for the coverage weights based on the degrees of the vertices in the updated graph. So for node 1 the degree is now 2, for node 5 its degree is 2, node 6 the degree is 3 and so on. So the coverage weight of the edge 1, 5 is going to be the degree of 1, which is 2, plus the degree of 5, which is also 2, 2 plus 2 minus 2. Now for this 5, 6, the coverage weight is degree of 5 is 2, the degree of 6 is 3, so 2 plus 3 minus 2 is 3. So that is how we find the coverage weights of the edges. And then again pick the edge with the smallest coverage weight, and you can break the ties in any order. So here 2 is a smaller value. Let us say I break in favor of edge 1, 5. So I pick 1, 5. So automatically 1, 6 and 5, 6 are ruled out from being considered further. So these are the 3 remaining edges. Each has a coverage weight of 2. So for example, for 6, 7 the coverage weight is degree of 1, so degree of 6, which is 1, plus the degree of 7, which is 3. So 1 plus 3 minus 2 is 2. So you can again pick any of these 3 edges. So let us say I pick 4, 7. And once you pick 4, 7, the other 2 edges cannot be considered. They are adjacent to it. So you continue the iterations until the graph gets completely disconnected like this to isolated vertices. So the edges that you pick are part of our maximal node matching. So the edges that we pick here are 2, 3, 1, 5 and 4, 7. So these are the 3 edges that are part of the maximal node matching. So as I said, in this graph we can find only a maximal node matching of 6 vertices and not 8 vertices, right? So we can come up with what is called the percentage of node matching, which is going to be 6 over 8. I'll show that in the next example, but you can also do the numbers for this example too. Percentage of nodes matched is 6 over 8, which is 75%. We really prefer 100% matching, but this cannot be determined for all the graphs. Okay, so only for certain graphs we can find 100% matching. For certain graphs we cannot find 100% matching. Okay, so let me stop and save this video.